Okay, hello. This is the rest of the concept of the atom video that you had started yesterday. This should have been the live session for February the 6th, the 7th. But since you both couldn't be there, I'll do a quick video and we will get you the notes and you can watch it on your own time and be able to do the next assignment. So when we talked about the concept of the atom before, we talked about what the atom was made of, and now we're going to talk about more details on how we do it and what the different parts we now have scientific names for. So for example, we start with the atomic number. The atomic number is the number of protons in the nucleus of the atom. Super important that you remember this. Proton number is atomic number. I would write this down in big letters. The atomic number identifies the element. No two elements have the same atomic number. Because all nitrogen atoms, for example, have 7 protons, the atomic number for nitrogen is 7. Any atom that is neutral, which is most atoms in their native state, shall we say, they are neutral, and what that means then is that the number of protons must be equal to the number of electrons. So when we talk about the atomic number, we talk about it as the number of protons in an atom, but technically, if we're still talking about the neutral atom, then it is also the number of electrons. So nitrogen has 7 electrons just like it has 7 protons. We also have something called the mass number. We know that in the nucleus of the atom we have not only the protons, but we also have the neutrons. So the mass number is the total of the number of parts in the atom that really have mass. We can ignore the electrons because their mass is so tiny. So the mass number is the number of protons plus the number of neutrons. Again, super, super important. And it's also super important that you can distinguish between the atomic number and the mass number quite quickly. So this is another thing that you want to write in large letters or in bright red or something. So a helium atom has 2 protons and 2 neutrons, so its mass number is 4. Here's where mass number and atomic number also differ. Atomic number, each individual atom has its own atomic number, but different elements can have their same mass number. So for example, with the carbon atom always has 6 protons, but we can have a different number of neutrons. A carbon with 6 neutrons is called carbon 12, 12 being the mass number of protons and neutrons. The carbon with 7 neutrons is called carbon 13, and carbon with 8 neutrons is called carbon 14. Carbon 14 and 13 are radioactive, and they become carbon 12 over time. We'll get back to that later. But here, the carbon 14 atom has a mass number of 14. However, nitrogen also has 7 protons and oftentimes has 7 neutrons. So it too has a mass number of 14. So carbon 14 has 8 neutrons, 6 protons. Nitrogen has 7 neutrons and 7 protons, still a mass number of 14. So mass number is not a characteristic, an identifying characteristic of an atom or an element, but atomic number is. Then we have isotopes. Isotopes are atoms that have the same atomic number, but different mass numbers, like what we were talking about before. So isotopes you can think of as being variations, like cousins, shall we say. Carbon 12, carbon 13, and carbon 14 are all isotopes of carbon. And in nature, we will find all of these. So we can't just say, well, one of them is the true carbon atom and one of them isn't, because really carbon is carbon. It just has a different number of neutrons here. So isotopes have the same number of protons, but different numbers of neutrons. So technically, rather than talking about carbon, we should be talking about what isotope of carbon we are referring to. Most of the time, we are talking about carbon 12 because that's the most abundant one. And we're going to get into how we know that shortly. Hydrogen also has 3 different isotopes. It has protium, deuterium, and tritium. It always has just 1 proton, but it can have 0, 1, or 2 neutrons. If it has 0 neutrons, it is called hydrogen 1 or protium. If it has 1 neutron, it is hydrogen 2 or deuterium. And if it has 2 neutrons, it is hydrogen 3 or tritium. Notice the 1, 2, 3 is not just the number of neutrons. The 1, 2, 3 is referring to the mass number because it's the number of protons and neutrons. So when we're looking at the isotopes, we have to make sure that we can distinguish what this all means. So if you take a look at this table, and let's talk about it in particular with hydrogen. Hydrogen is 1 proton, we know that, so let's just go ahead and put 1, no matter what it is. Hydrogen always has 1 proton. Hydrogen also has 1 electron. Remember on the last screen we said that hydrogen 1 has no neutrons, hydrogen 2 has 1, and hydrogen 3 has 2. So our mass number then, if we add these two columns up, our mass number is 1, 2, and 3. Our atomic number, remember, is the same as the number of protons we have. So the atomic number for all 3 isotopes of hydrogen are all 1. So one more time, atomic number is the same as the number of protons. Mass number is the number of protons plus the number of neutrons. When you have isotopes, it's the number of neutrons that changes, not the number of protons. There's a picture of how this looks on the next screen. If I'm talking too fast, make sure that you pause and take some notes along the way. So let's look at the 3 different isotopes of neon. Notice that they all have 10 protons. They all have 10 electrons, but their numbers of neutrons change. So you have neon 20, neon 21, and neon 22. Again, the number 20, 21, or 22 refers to the mass number. And so this is what it looks like. Each of the each of the nuclei look a little bit bigger as we go on. All 3 of these have the same number of protons, which is 20, and the same number of electrons, which is 10, but different numbers of neutrons. Because isotopes of an element have different numbers of neutrons, they also have different mass numbers. But chemically speaking, isotopes are the same because it's the protons and the electrons do reactions. Neutrons are neutral, they don't react with other things, but protons and electrons do. So electrons are the subatomic particles that are most responsible for the chemical behavior of an element. And because the element wants to be neutral, the number of electrons depends on the number of protons. Okay? So one more time, isotopes have the same number of protons and electrons as each other from the same element, but they have different numbers of neutrons, and they act the same chemically. So all the carbons act the same, all the neons act the same, all the hydrogens act the same. So let's look at this. Let's say, all right, if we have a mass number of 20, then that means that we are talking about neon 20. Its atomic number is 10. From a couple of slides ago, we know that its proton number is 10. Proton number does not change, so the atomic number does not change. So the number of electrons don't change. And then the number of neutrons, well, if the mass number is 20, 10 plus what is 20? Well, 10 times 10 plus 10. And then 11, so this one must be neon 21. And the third one is neon 22 with a number of neutrons of 12. If you look at all of the isotopes, if you were to take a look at the isotopes, you could fill in a chart like this for all of them. And it's important that you understand how these work so that when we get into doing chemical equations, you can know which isotope we are talking about. Whoa, 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 whoa. All right, so shorthand notation. I don't want to have to always write everything out like that. So instead we use shorthand notation that you've seen a little bit of before when you've been reading. So the composition of any atom can be represented in shorthand notation using the atomic number and the mass number, because these are the things that tell you about the atom itself, tell you the number of protons, neutrons, and electrons. So for example, this is gold. Au is gold, obviously not an English abbreviation. So the two letters, the first one is capitalized as per the criteria. The second one is lowercase. The atomic number is the subscript, this one. Okay. Remember, again, the atomic number is the number of protons. That goes on the bottom. The mass number is the superscript. The mass number, remember, is the number of protons plus the number of neutrons. So by knowing this is gold, 79,197, we can find out how many neutrons this atom of gold has by simply taking the mass number of 197 and subtracting the number of protons, 79. If we subtract that out, we end up with 118. So there are 118 neutrons in this atom of gold. So then the question becomes, well, are there more isotopes of gold than just this, or what? And right now, we're not going to worry about whether there are more isotopes of gold or not. There aren't. But this is the notation that you will need to use. Sometimes it's also written as 197 Au 79, so you may see it written like this as well. It doesn't really matter which way you put it. On Blackboard, sometimes you're going to have to write it like this, 197 Au 79, because it won't accept two numbers on the left. But either way is actually acceptable in chemistry. So let's take a look at this. Write the symbol for the three isotopes of carbon, carbon 12, 13, and 14, using superscripts and subscripts. If you check out a periodic table, you will know that carbon has an atomic number of 6. So we can say carbon, atomic number of 6, mass number of 12. Or carbon, atomic number of 6, mass number of 13. Or finally 6 and 14. The neon atoms that we were just looking at, we could do the same thing. Neon 20 is 1020. Neon 21 is 1021. And neon 22 is 1022. Simple nomenclature here. You just have to remember the two things. Number one, keep in mind that the subscript here is going to be smaller. This is the atomic number, which of course is the number of protons. And the top number is your mass number, which is your protons plus your neutrons. So if I want you to calculate the atomic mass, it is based on the idea that the proton and the neutron both have a mass of 1 AMU. Okay? An atomic mass unit is what an AMU is. It is by definition 1/12 the mass of a carbon-12 atom. Carbon-12 atom has 6 protons and 6 neutrons, therefore its mass is set at 12 AMUs. In other words, 1 AMU is the mass of 1 proton or 1 neutron. The atomic masses in our periodic tables, however, are not individualized to each isotope. It is a weighted average based on the amount present or their percent abundancy in nature. So the average atomic mass reported is not a whole number because it represents an average of all of the naturally occurring isotopes and their percent abundance, where the isotopes that have more abundance in nature are going to be heavily weighted on the average because they're going to have more mass relatively to what's out there on Earth, in nature. So let's take a look at this at hydrogen. All 3 isotopes of hydrogen are shown here, okay, protium, deuterium, and tritium. And almost all naturally occurring hydrogen, 99.985%, is hydrogen 1. So the other two isotopes are trace elements, so barely any of them there at all. The atomic mass of hydrogen in this table says that it is 1.0079. It is very, very close to this one because that's the one that's most abundant. So in order to figure out how to get that number, we have to look at the natural percentage abundances, the mass in AMUs of each isotope, and then we have to do some multiplying. So let's get to this. So you need these three things. You need the number of stable isotopes of the elements, 1, 2, 3, 5, 12, whatever. You need to know their number, like what are they? Carbon 12, carbon 13, carbon 14, that sort of thing. You need to know the mass of each isotope, and you need to know the natural abundancy, percent abundancy of each isotope. So how often are they found? So, for example, the element copper has naturally occurring isotopes of mass numbers 63 and 65. The relative abundancy of copper 63 with a mass of 62.93 is 69.2%. So 69.2% of all copper found in nature is copper 63. Copper 65 has a relative abundancy of 30.8%, and its mass is 64.93 AMU. So to calculate the average atomic mass of these numbers, you have to basically do percentages and add for the two. So in other words, I want to say that I'm going to have my 62.93 AMUs, and I'm going to multiply that by my percentage of 0.692. And that will give me part of my average. Then I take the other one and I say 64.93, and I multiply it by its percentage of 0.308. And I get a number there. Now, keep in mind that in order to do this correctly, you have to make sure that you have changed your percentages to decimal points. So this first one comes out to be 43.54756, and the second one comes out to be 19.99844. So we have our relative weights of the two isotopes of copper. And if we then add them together, we end up with 63.54600. So, okay, well, what does that mean? And why is this 5 and this 9 underlined? Well, the 5 and the 9 are underlined to remember that your percentages here were actually only to the tenths place. So in terms of significant figures and what is reported in periodic tables, that's what we're talking about. So if we look up copper on the periodic table, we see that on the periodic table, the atomic mass that is reported is 63.546. Your periodic table may not go that far, but it might go farther. So we then say, all right, that's what our number is. When we're trying to find out the atomic mass, the average atomic mass of an element, we don't really worry too much about significant figures. They are important, but right now we're not going to stress over them. So take a quick look at this one. 4 isotopes of lead are shown, each with its percent of mass abundance and its composition of its nucleus. Using this data, calculate the approximate atomic mass of lead. All right, well, let's see. I know that 51.55% is is lead 208. So I would do 208 times 0.5155, and then I would have 207 that I would multiply by 0.2082, and I would have 206 times 0.2626, and then 204 times 0.0137. Now notice that these numbers are all given in whole numbers. So your 208, 207, 206, and 204. If you were to look those up, you'll get more decimal points to it. But for the sake of making sure that you know how to do this, this is what we would do. We would find out all of these products, and then we would add them together. And here is where you want to take a look at sig figs. So if we take a look here, we have all of the numbers multiplied. We add them up. We get 207.2118 AMUs. And we round this to 207.2 AMUs. And you could say, but wait a minute, these are all whole numbers. Why did you round it? And it gets back to, how do we know what these numbers are? These are counted values. That's how we know what these numbers are. So this hopefully has explained to you how to calculate the mass numbers of, the atomic mass. These calculate how the atomic mass of the average, shall we say, of all of the isotopes that are found in nature. If you have any questions, please make sure you email me since I wasn't able to explain this to you live. Bye for now.